Hello there, this is Daniele from Toolchefs, and in this video I'm going to give you an overview of Atoms Crowd. So for any software, knowing what's happening under the hood with Atoms is going to give you greater control on your simulations, and you will be able to achieve better results with less effort. So it's very important to understand really what's happening under the hood, especially because Atoms is a very open framework. If you know any Python or C++, it's very easy to get access to any entity of the simulation during the simulation. So in Maya, for instance, you can do it in the script editor. In Unreal, you can use Blueprint for accessing that information. In Houdini, you could use Vex or Python and so on. So it's quite important to actually understand what's going on. So the first thing that we're going to have a look at is the data flow. So you can find also this image from the documentation. But as you know, Atoms is basically a standalone framework, as we just said, and we just use softwares like Unreal, Maya, and Houdini to collect data. So these will be the assets that we want to use, the setup that the user is creating, and then we send all this data to Atoms. And then Atoms will evaluate the simulation, and then we'll send back the data to these softwares, and then these softwares will display the agents. So we'll actually, you will see, your agents walking or running, going to a point, avoiding each other and so on. So it's important to understand that the actual simulation is happening in Atoms, and Atoms is not depending on any of these packages that we support. What we do instead is we create plugins that basically acts like as a bridge between Atoms and the host application. So basically, usually from Houdini and so on, you would start exporting assets. So this would be skeleton, geometry files for defining the agent types. You can also export, of course, animations, and we support different numbers of file formats. So we support FBXs, we support USD, we support Alembics. We support also our own proprietary formats that are Atom Skeleton, the Atom Scale file. But while for animation, we mainly use FBX. The cool thing about Atom is because it's so open, you can also create your own readers. So if your company has special file formats, you can still, if you know C++, you can create new readers. So you can still use your own proprietary formats with Atoms, which is pretty cool. Then from Atoms, what you can do, you can start, once your simulation is built, you can start exporting files. So this could be FBX, Alembics, or USD caches. You can also export different metadata files. So metadata is the basic entity of Atoms. So it's basically what we use for, as a data storage. So it can be of different types. So it can be an integer, it can be a double, it can be an image, a curve, a mesh, and so on. So we have a lot of different types. And the cool thing about Atom is that many of the entities that we run during the simulation, like agents, joints, poses, and so on, they can have metadata attached to them. And we use metadata during the simulation for driving the simulation as well, and we're gonna see that later in this presentation. So these metadata files, again, they can have different purposes. We can also export them, for tools like the blend shape animation, the blend shape anim manager, I think it's called, from Maya and so on, for driving animations within Atoms for the blend shapes. But we also have, we use it also in different other places. For instance, our geos file, which is the file that we use natively for supporting geometry, is actually a metadata file. So that would be a map metadata, which is basically like a dictionary, which contains all the information that we need for skinning the geometry at simulation time or render time, and display it in the viewport or at rendering time within the render engines. Also, another thing that of course you can support export from Atoms is Atoms caches or USD crowd caches, and then you can also import them back in Atoms and edit the cache afterwards. So Atoms is a great tool also for post-editing caches. You can use even USD caches that weren't exported by Atoms. So for instance, you can export a USD cache from Houdini and then import it in Atoms, and this is a great way for actually then manipulating the cache afterwards. because you can other than just changing maybe variations or changing the position or rotation of the agents, you can actually re-simulate agents. So you can change their paths, adapt them to a different ground and things like that, which is pretty cool. Once you have an Atoms or USD cache, then you can also render with an external render engine like Arnold or Renderman and so on. Also, the Atoms caches can also be imported in other applications like Claris. Then we have Katana, Gaffer support, and so on. So this is basically pretty much what you need to know about the data flow. So Atoms, once again, I would like to point out that Atoms is a great tool for exchanging data between software. So typically in VFX companies, especially it happens that these companies, they start building tools for bringing in these data in different applications. But with Atoms, we try to do everything, like all these job for you. So you will be able to export your simulation in Maya and then import them in Houdini and vice versa. Same thing also for Unreal for sure. Okay, so now let's have a look at the simulation. So don't get scared while looking at this graph. This is also in the docs. But basically, the simulation is mainly made of two things. So simulation events and agent groups. Simulation events, typically we have two different simulation events that we use in a standard VFX or even game workflow. And they are animation clips and agent types. So agent types, they are basically the definition of agents. So they will contain usually a skeleton, some geometry, maybe a ragdoll definition, a character definition, a characterization definition, which is what we use for retargeting. And then we have animation clips, which are what basically we use for registering animation in softwares like Maya and Houdini. We usually get this animation from files. This would be FBXs or USD. In Unreal, instead we use the animation sequence asset. So these simulation events are used usually for registering assets like agent types, animation clips, and so on. And then we have the agent groups, which are what actually run the simulation. An agent group usually is made of agents and behavior modules. So agents, because agent groups act as a container for agents, and these agents each one of them will have a separate dependency graph and a set of metadatas. So the dependency graph is what is used during the sim to actually build the pose of the agent. So it's not really like a brain, but it's more like having some inputs will actually generate the pose for your agent at each tick or frame. And then each agent has like a set of metadatas that can be user defined, so you can create your own, or there are some default ones that you can find a full list in the docs. And depending on the values of these metadatas, the agent will behave differently. So it could change animation, it could change pose of a joint, it could really do various things depending again on which metadata and which value. And we're gonna see another example later. Then we have the behavior modules. So basically this part, so this top part of the agents, you don't actually see much of it because the dependency graph is built by the behavior modules, and also the metadatas are edited by the behavior modules. You will start playing with the metadatas if you start using Python or Vex or write your own C++ behavior modules, for instance, or even if you use Blueprint in Unreal. And then the dependency graph is something that usually behavior modules edit. So for the behavior modules, each agent group has a stack of behavior modules, and all of them they can generate agents, they can edit the agent, they can by edit the agents I mean they can modify the dependency graph or change the metadatas on the agent. And in the way you stack them is important because of course they will be evaluated in order. And each one of these behavior modules, they will do something during the simulation or at the beginning of the simulation, and depending on how you put them, you stack them, and the inputs that you the value that you input as their attributes will actually edit the simulation. So this is basically how the simulation works. If you want to know more about the behavior modules, a behavior module is basically, if you want to think of it, is like more like a set of functions that are getting called during the simulation at different stages. And here I've listed some of them, and I've put them pretty much in order, in the order in which they are called. So the init simulation function is going to get called at the beginning of the simulation. So if the behavior module needs to do anything at the beginning of the simulation, it will do it. It will do it there. Then we have the agents created, which is called whenever an agent is created. The agents killed whenever an agent is killed. Preframe is getting called at the beginning of each frame or tick before the agents are created. Then we have the init frame, which is called after the agents are created, but before the frame is evaluated or tick is evaluated. And then we have the end frame, which happens after the tick or frame evaluation, the end simulation, and the reset simulation. And it's important to know that you remember we said before that we have the node graph of the agent that evaluates the pose. That happens basically at this stage, so between the init frame and the end frame, right here. So you can basically change the metadata of the agents. For instance, you could change the direction metadata, which is what drives the agent. It will actually tell the agent to go in this direction or in that direction and so on. And the agent will actually turn, will point to that, will actually follow that direction. You can change in the end frame, for instance, the pose of a joint, because if you change the pose of a joint before the computation of the dependency graph of the agent, basically whatever happens, so whatever pose you're gonna set on a joint before that happens is gonna be overridden by the node, that dependency graph. So whenever you need to really to maybe change the pose of a joint or the position or the rotation, you should do that at the end frame stage. So here I've prepared some examples. So usually, we have different kind of modules. So we have layout modules, we have animation modules. So layouts are basically what we use for creating agents. Animation is what is used for playing animation. Then we have usually, directional modules, which change the direction of the agents. And then other modules that are called like the pose modules, which change the pose of the agent. So we have other types of behavior modules, but I just put them here, these ones here, just to tell you that basically not all the behavior modules will do something at all of these stages. For instance, the grid layout, what it does is just builds like a layout generator at the init simulation for creating your agents. If it's dynamic, also it's gonna do something at the pre-frame stage, but like if you don't use the dynamic option, you're just gonna do something at the init simulation, and then it does something at the agents created, just because if you don't create a state machine or a clip operator, basically it does something to the graph so that at least you can have the agents there and maybe move them around and so on. Then we have the state machine. The state machine is the usually it's used for playing a state machine on top of an agent. And this one, for instance, it just has something at the agent's created stage, because at this stage we'll actually build a state machine for the agent. So it will actually build all the nodes that they're used in that dependency graph for building the end pose. So unless basically in most of our example we have the grid layout, and then we have the state machine following the grid layout. And by just having these two modules, you'll see your agents maybe going in a straight line, but at least they will be playing an animation, and you'll be able to switch between states. The init frame is basically the init frame stage is where we get all the attributes from the state machine, and then we pass basically the values that the user just given us as input to the operators or to the dependency graph or to the metadatas in case anything was changed. Then we have the flocking. The flocking, because it's just a directional modules, we just do something at the init frame, because it's basically, as again, in the init frame is where you would change the direction of the agents. So in this way, then we can compute the pose with the right direction. And then the AKM is just something that basically is a module for applying an AKE on a chain of joints, and then basically what we do there is just we implement just the end frame. So in here at the end frame, after the node network has, sorry, the dependency graph has evaluated the pose. Then we apply some transformation on the joints just so that we apply this IK on the joints of maybe an arm or a leg or whatever you want. Okay, so the next one is an example. So again, we said before that the agent has metadata and it has a dependency graph. It's something that I haven't said yet is the dependency graph, usually it has like different types of nodes. So usually we have nodes and operators. So nodes can be any nodes like the time, or it can be the time node, or it can be a math node like a matrix multiplication and so on. But then we have also the operators, which are the nodes that actually have as output a pose port, which basically is the so it means that basically these nodes can actually output a pose for the agent. And the last operator will actually output the pose that is being applied to the agent. So here, for instance, we have the clip reader, which is our operators that read a clip. The state machine is the operator that plays with, make sure that the right state is being played. Then here we have a merge node that will get the two clip readers, and then by using the input of the state machine, will actually merge so that we actually get the right animation depending on the input of the user. Then we have the pelvis, which is what does the terrain adaptation, and the foot, which does the foot locking. I've oversimplified this dependency graph just to give you an example. If you use a state machine, even the standard one, the graph is way more like the standard one from our man. The graph is way more complicated than this one. So this is just to give you a quick explanation. You will find probably I don't know, way more clip reader nodes. We'll find other merge nodes before the state machine. So it's like that. There's a lot of things going on. So this is just to give you an example. So this is again here I've written grid layout and state machine. And this is because this is actually the graph that you would find whenever you create a grid layout and a state machine. The grid layout wouldn't create any dependency graph, dependency node, but the state machine will actually build all of this for you. So this is to say a few things. So before we said that when you change metadata, then you could change the behavior of the agents, where the agent is going, and so on. And this is true when, for instance, you change the frame rate metadata. The frame rate metadata is used by the clip reader. So you see here we have the clip reader here and there. And when you change that metadata, then the speed of the clip, whenever we read it, changes. So if you set it for 2, for instance, it's going double of the speed. If you set it to 0.5, it goes half of the speed. The frame rate, you could set it from the state machine module, or you can create an add metadata module that is used for setting custom metadata, or even metadatas that are built in Atoms, for actually changing the metadata, that specific metadata. So if you change the frame rate, I've written with the F in lowercase and R in uppercase, because these metadata, they are case sensitive, so it's quite important the way you write them. But anyway, if you change the frame rate, again, that is basically the result that you would get. And the frame rate metadata is used by the clip reader. Then we have the state metadata, which is used by the state machine. So whenever you, for instance, change the state in a state machine module, or with an add metadata module and so on, or even with a Python script, you actually pass this metadata is read by the state machine. It's important to know that for this specific case, the state machine, when we change the state, it keeps a stack of the actions that we perform. So when we change this state metadata, and it's not going to change the state straight away, because it will need to get to a transition frame for the animation clips. I won't go and explain exactly what transition frames are. I would actually suggest to check the documentation, but basically they are they tell the state machine when a clip can transition from one state to another, so to the next clip. So when the state machine finds basically a different state, then we'll try to value. So state again is an integer. So for instance, we say we go from 0 to 1. When the state machine finds that the state metadata has changed, they will actually get this new value and put it into this stack. And then it will, as soon as it hits a transition frame, it will actually start transitioning. and then we'll keep playing that state, the last state we passed as input, until you change, the user changes again the state. If you want to know the actual state that is being played, because this is something quite useful sometimes, you can actually check the current state metadata. So again, this is quite important to have to use the lowercase for the C and uppercase for the S. And so basically this is it for this quick overview. There are more information on the web, on the documentation. And if you have any questions, feel free to send us an email or write on our Google group, and we'll make sure to answer to all your questions there. Thanks for watching. Bye bye.